This is my Comp 4105 project presentation. The title is Exploring Prompt and Parameter Effects in GPT-2 Dialogue Agents. In this work, I treat GPT-2 as more than just a generator. It's an agent that reacts to prompts and behaves differently depending on how we design them. Even with the same model, small changes in prompt, phrasing, or sampling settings can lead to very different outputs. In this video, I'll take you through the motivation, setup, experiments, and key findings. Let's begin. GPT-2 is a powerful language model, but its output can change a lot, not because the model changes, but because of how we interact with it. Two key factors affect the results: the prompt wording and the decoding settings like temperature and top K. For example, when asked, what's the capital of France? Low temperature like 0.2 gives Paris. But at 1, you might say, that's a fascinating question. Let's travel to Paris. Same model, different tone, and sometimes even different accuracy. So the way we phrase prompts and configure sampling directly impacts fluency, relevance, and correctness. That brings us to the core question. How do prompt design and decoding parameters affect GPT-2's output across different tasks? This project is built to explore that through systematic experiments. How do prompt design and decoding parameters like temperature and top K affect the output quality of GPT-2? On one side, we can tune parameters to control randomness and creativity. On the other, we can craft prompts to guide intent and focus. To explore this, I built a modular GPT-2 agent using Hugging Face transformers. It receives prompts and generates outputs in different settings, including a real-time GUI for interaction. I tested it across 3 tasks: dialogue generation, question answering, concept to sentence generation. To evaluate the outputs, I use both fluency and semantic metrics like perplexity, bird score, meteor, and distinct. And the GUI also helped observe qualitative patterns in live settings. Together, this setup allowed me to run systematic experiments and study how each design choice impacts generation quality. To study how prompts and parameters affect GPT-2 outputs, I built a modular pipeline with 5 stages. First, I generated 150 prompts across dialogue, QA, and concept tasks using public datasets with consistent templates to ensure control. Then I ran GPT-2 under different sampling settings: temperature from 0.2 to 1, top K from 0 to 80, and top P fixed at 0.9. For each prompt, 5 outputs were generated to capture variation. I measured the fluency using perplexity and filtered outliers. I also computed bird score for semantic similarity, meteor for lexical overlap, distinct 1, 2 for diversity, and QA accuracy. Results were visualized with charts showing how quality varied across tasks and settings. The whole pipeline is reproducible and modular. In this setup, GPT-2 acts as a language-based agent. Prompts represent the environment, and its outputs are actions. In the GUI, responses can influence future inputs, forming a simple feedback loop. Prompt design is a core part of this project, as prompts define the input environment for the agent. To test how decoding and phrasing affect outputs, I use 3 task types. First, dialogue prompts simulate real conversations and test GPT-2's ability to generate context-aware responses. Second, question answering prompts evaluate factual accuracy. Can the model give correct, concise answers? Third, concept to sentence tasks test creativity. The model receives 3-5 concepts and must generate a coherent sentence. All prompts were auto-generated from real datasets: daily dialogue for dialogue, SciQ for QA, and CommonGen for concept tasks. Each task has 50 prompts saved with reference outputs, ensuring a balanced and repeatable evaluation. Once the prompts were ready, I used GPT-2 Medium from Hugging Face to generate responses under different decoding settings. I focused on temperature and top K, 2 parameters that shape how creative or controlled the output is. Lower temperature gave more focused responses, while higher values introduced diversity. Similarly, top K sampling adjusted how many next token options the model could choose from. I fixed top P at 0.9 and varied the other 2 parameters across several levels. For each prompt, I generated 5 outputs to capture randomness and compare across settings. All generations were handled through a Python script where prompts were fed into the model, decoded, and saved along with metadata. The results were stored in a CSV file, which served as the input for the next evaluation stage. After generating responses with GPT-2, the next step was to evaluate their quality, especially fluency. To do this, I used perplexity, a standard metric in language modeling. It measures how surprised a model is by a given text. Lower perplexity means the text is more fluent and predictable, while higher values suggest it's awkward or disjointed. I reused GPT-2 to score its own outputs. Each generated response was passed through the model again, and perplexity was computed using Hugging Face's evaluation module. To make the results more reliable, I processed texts in batches and removed the top 5% of scores, which were often outliers or empty generations. All scores were collected into a central data frame for later comparison across tasks and decoding settings. In addition to automatic evaluation, I built an interactive GUI using Tinkinter to test the agent in real time. It simulates a local language-based agent that can respond to user input across all three task types: dialogue, QA, and concept generation. Users can select the task mode and enter a prompt. The agent responds immediately, and all outputs are generated using fixed decoding settings: temperature 0.7, top K 50, and top P 0.9. This interface was mainly used for qualitative analysis to see how GPT-2 behaves under different prompts and whether its responses feel coherent or controllable in live interaction. It offered insights that automated metrics alone couldn't reveal. To evaluate GPT-2's output across different prompts and parameter settings, I used a set of automatic metrics, each focusing on a different aspect of quality. Perplexity measures fluency and model confidence. Lower scores mean the output is more natural. BERT score evaluates semantic similarity using model embeddings, which is helpful when the wording differs from the reference. Meteor checks lexical overlap, and distinct 1 and distinct 2 assess how diverse the output is by counting unique unigrams and bigrams. For QA tasks, I use accuracy to see if the generated answer matches the expected fact. I excluded empty generations and outliers and reported median values to improve robustness. Together, these metrics give a more complete view of fluency, meaning diversity and factual correctness. This slide shows the overall results across all prompts and decoding settings. Perplexity varied widely, suggesting that while some outputs were fluent, others were more unpredictable. BERT score averaged around 0.81, meaning the outputs were semantically close to the references. However, distinct 1 and distinct 2 were low, indicating repetition, and both Meteor and QA accuracy were near zero, likely because GPT-2 rarely matched the reference text exactly, especially for short, factual answers. Overall, GPT-2 produces fluent and plausible responses, but often drifts from precise answers. Sampling boosts diversity, but can reduce accuracy. No single metric gives the full picture. Evaluating fluency, meaning, and correctness together is essential. These results confirm that both prompt design and decoding settings have nuanced and sometimes conflicting effects. This section summarizes the performance of GPT-2 across the three task types. For the concept-to-sentence generation task, GPT-2 performed well in terms of meaning. We see a relatively high BERT score of about 0.82, which shows strong semantic alignment. However, Meteor is nearly zero, suggesting little word-for-word overlap. Perplexity becomes very high at temperature 1, meaning the text is less fluent when randomness increases. In the dialogue generation task, GPT-2 shows its best BERT score around 0.83. This makes sense as the model was pre-trained on dialogue-heavy data. However, distinct N scores are low, so replies tend to be repetitive. Meteor is again low, showing that although replies are coherent, they rarely match the reference wording exactly. For the question answering task, some runs achieve non-zero QA accuracy, so the model can give correct facts occasionally. BERT score is slightly lower, around 0.8, likely due to short answers. Perplexity is more stable than in other tasks, suggesting more consistent fluency. Overall, these results show that GPT-2's output quality varies across tasks. No single decoding strategy performs best for everything. Task-specific tuning is essential. Now that we've reviewed task-specific results, we can summarize some key trade-offs. Concept prompts encourage creativity. GPT-2 can combine abstract ideas into coherent text, but outputs become less fluent at high temperatures. So there's a clear trade-off between originality and fluency. In question answering, the model sometimes gives correct facts, but accuracy is inconsistent and exact matches are rare. It shows potential, but factual reliability remains limited. Dialogue prompts yield a strong semantic alignment. Bird score is high, but replies are often short and repetitive, likely due to the model defaulting to safe responses. Overall, no single setting works best for all tasks. Each prompt type highlights different strengths and limitations, underlining the need for task-specific tuning. In this slide, I focus on how the top K parameter affects GPT-2's dialogue performance. On the left, we see that perplexity is lowest when top K equals 50. This suggests the model is most fluent and confident at that level. Too small or too large a value harms fluence either by limiting choice or making output unstable. On the right, bird score also peaks at top, K equals 50, reaching 0.83, the best among all settings. This means semantic alignment is also strongest at moderate sampling. So top K equals 50 provides the best trade-off between fluency and semantic relevance. Going beyond that slightly increases diversity, but at the cost of coherence. This shows how decoding parameters must be carefully tuned, not chosen randomly and adapted to each task. In this slide, I illustrate the effect of temperature using a real example from the interactive agent. The prompt is, what should I do if I feel sad? With temperature I equals 0.2, the response is, don't be sad, you're not alone. It's correct and polite, but feels generic typical of low temperature outputs, safe but dull. With temperature equals 1, the answer becomes, don't be sad. You have nothing to be sad about. Remember, one is not responsible for one's feelings. It's more expressive and thoughtful, but also longer and potentially off topic. Um, this shows the trade-off. Low temperature gives control and consistency. High temperature increases creativity, but risks losing focus. So temperature needs to be tuned, depending on where we want safe or creative outputs. Now that we've seen the results, let's reflect on what they tell us. Starting with decoding parameters. Lower temperature and smaller top K produce safer, more predictable outputs useful for factual tasks, but they limit creativity. Higher values bring expressiveness, but increase the chance of incoherent or off-topic results. This trade-off is most visible in concept generation, where we want novelty, but fluency drops at extreme settings. So decoding settings act like behavioral controls for the agent, tuning how cautious or bold it is. As for prompts, clear templates like question or dialogue help guide the model's behavior. They align the response better with intent and shape the tone and scope. Different tasks need different prompt. Style structured prompts work for QA, but open-ended ones support creativity. The key takeaway: there's no universal best setting. Good generation depends on both the task and how we design the input. Before concluding, I want to briefly reflect on the rigor of this experiment. To ensure reproducibility, I used the fixed random seeds, defined all decoding settings in a single config file, and generated 5 outputs per prompt to reduce randomness. Outliers in perplexity were removed, and invalid generations were filtered out before scoring, so only meaningful outputs were analyzed. That said, there are limitations. Bird score and other metrics don't fully capture output quality, especially surface accuracy or nuance. There was no human evaluation, and GPT-2 is a relatively small model compared to more recent ones. Also, the datasets used don't cover all real-world dialogue scenarios. Despite these, the setup remains useful for exploring how different decoding settings impact generation quality in a controlled and repeatable way. As I wrapped up this project, I realized that many of the patterns I observed echoed existing research, but also revealed new insights. Take decoding, for example. I used to think of temperature and top K as minor tweaks, but they strongly shaped fluency, repetition, and even tone, confirming the creativity versus coherence trade-off described by Holtzman et al. Prompt design surprised me too. Small changes like adding question or dialogue had a big impact on how focused the responses were, aligning with the prompt as program idea from Brown et al. I also found distinct N useful for detecting repetition, much like Li et al. Work on dialogue diversity. Looking ahead, I see several extensions. Exploring top P sampling in combination with top K, trying newer models like GPT 3.5 or LLMA2, and adding human evaluations to complement metrics like BERT score. I'd also like to explore how prompt phrasing affects factual accuracy, or test how RLHF models respond differently. Overall, this project deepened my understanding of how much generation quality depends not just on model size, but on thoughtful prompt and decoding design. Looking back, one of the biggest surprises was how much prompts shaped the output. At first, I thought it was just about wording, but it's really about framing. Adding simple cues like question or dialogue made responses more aligned and focused, almost like giving the model a clearer role to play. I also saw how sampling parameters reshape behavior. Lower settings made outputs safe but bland. Higher ones brought creativity but risk losing coherence. There's no single best setup, it depends on the task and desired style. As for evaluation, metrics like burst score help, but they don't always match human judgment. Some high scoring responses still fell off. Reading outputs directly through the GUI helped me catch issues that numbers missed. Finally, task type mattered more than expected. QA was fairly stable. Concept tasks were creative but less fluent. Dialogue was the hardest, often repetitive and shallow. This project showed me that prompting and decoding aren't just settings, they shape how the agent behaves. That's the end of my project. Thank you for taking the time to watch